So example number 2. Example 2. All right, find the max and min of f of xy equals x squared plus 2y squared minus x on the closed disk of radius 1 centered at the origin. Centered at the origin. Okay, so what we want to do, we have this, the unit, okay, so now we're considering the entire region, and it's a closed region, okay, so we're considering the interior and we're considering the boundary. That's all that's happening here. Okay, so let's see, equals 0. So this is our function, and we want to find the maximum and minimum values on this region. Okay, so we have a couple of things going on here. One of the things that we're going to do is so this is kind of a max-min problem and a Lagrange multiplier problem. The Lagrange multiplier problem will usually apply to this boundary here because we have an equation for that boundary, which is just x squared plus y squared equals 1, or x squared plus y squared minus 1 equals 0. As far as the interior is concerned, well, we just treat it like any other max-min problem. We see if we can find a critical point and take it from there. So let's go ahead and do that first. Let's deal with the interior. So let's find the gradient of f, and we will set it equal to 0 to see where the critical points are. So the gradient of f is going to be 2x minus 1. That is the derivative with respect to the first variable x. And then we have, let's see, 2y squared. I'm sorry. This is 2y squared. So our derivative with respect to y is going to be 4y. Okay, so now we want to check to see where these are equal to 0. So we've got 2x minus 1 equals 0, and we've got 4y equals 0. Well, this implies that y equals 0, and this implies that x equals 1/2. So at the point 1/2, 0, the point 1/2, 0 is a critical point. So let's go ahead and just find the value of f at that point. When I evaluate f at that point, f of 1/2, 0, I go ahead and put it into f, and I end up with minus 1/4. Okay. So that's one possible value. That's a critical point. That's on the interior. Now we can go ahead and deal with the boundary. All right. Now let's check the boundary. So the boundary is, so g of xy is equal to x squared plus y squared minus 1, and that's going to be one of the equations. We're going to need to set that to 0. So let's go ahead and find the gradient of g. Gradient of g is equal to, well, it's going to be 2x, and it's going to be 2y. Okay. So 2x and 2y. So now we're going to go ahead and set the gradient of f equal to lambda times the gradient of g. And what we get is 2x minus 1 and 4y is equal to lambda times 2x and 2y, which is equal to 2 lambda x and 2 lambda y. So the two equations that we get are let me do this one in red actually, so that I separate out the equations that I'm going to be working on. Again, this is all about solving simultaneous equations. I get 2x minus 1 is equal to 2 lambda x. I get 4y is equal to 2 lambda times y. And let me make sure that I make everything clear so that we don't make the same mistake we made last time. So this is 2 lambda y. And of course we have our equation x squared plus y squared minus 1 equals 0. That's the constraint. So now I've got 3 equations and 3 unknowns, x, y, and lambda. Okay, so let's deal with case 1. Case 1, let's take lambda equal to 0. So case 1, lambda equals 0. Okay. When I set lambda equal to 0, what's actually going to end up happening is I'm just going to end up getting the previous answer. So that's not an issue. So now let's deal with case 2. Case 2, where lambda does not equal 0. Okay. So one possibility for here, so when lambda does not equal 0, now there are some subcases that I have to consider. The first subcase that I'm going to consider is y equal to 0. Okay, when I set y equal to 0, then I'm going to get x squared plus 0 squared minus 1 equals 0. I'm going to get x equal to plus or minus 1. Therefore, I'm going to have the points 1, 0, and minus 1, 0. Well, at 1, 0, when I evaluated at f, I'm going to get 0. And when I evaluated at minus 1, 0, when I evaluate f, I'm going to get the value 2. So now I've got 1, 0, minus 1, 0. These are the values, and I also had that other point, that 1/2 0, that I found from just working on the interior of the disk, and the value was, I think, negative 1/4 or something like that, whatever it was. So now that's the case where lambda does not equal 0 and the case where y does equal 0. Now we want to consider the other case where y doesn't equal 0. Okay, so again, it seems like there's a lot going on, but usually you can make sense of it by just spending some time with it. So y does not equal 0. Well, when y does not equal 0, 4y equals 2 lambda y. That means lambda equals 2, 4y over 2y. Let me go ahead and write that out actually. Lambda equals 4y over 2y equals 2. Well, when lambda equals 2, this implies that 2x minus 1 equals, well, the equation is equals 2 lambda x, right? So 2x minus 1 is equal to lambda equals 2. It's equal to 4x. So I'm going to get 2x equals minus 1, x equals minus 1/2. So when x equals minus 1/2, now when I put that into my x squared plus y squared minus 1 equals 0, when I put it into here, I'm going to end up with the following. It's going to be minus 1/2 squared plus y squared minus 1 equals 0. I get 1/4 plus y squared minus 1 equals 0. I get y squared equals 3/4. Therefore, y equals plus or minus rad 3 over 2. Okay, so now my other points. X is minus 1/2, positive rad 3 over 2, and I get minus 1/2 minus rad 3 over 2. When I evaluate these at f, I'm going to end up with 9/4 and 9/4. So I've got 9/4, 9/4, negative 1/2, 0. I check all those points to see which one is the maximum, which one is the minimum. So the max takes place at the points negative 1/2 rad 3 over 2 and negative 1/2 minus rad 3 over 2. Value is 9/4, and the minimum takes place at the original point that we found, which was not minus 1/2, at 1/2, 0, and that value was, let me see, what was that value, if we can recall, minus 1/4. There we go. So this is our solution. I'll go ahead and put f here when we evaluate f. So at this point and this point, our function achieves a maximum, and at this point, the function achieves a minimum. That's it. So clearly there's a lot going on, a lot of things to sort of keep track of, but we are solving, several equations in several variables, and this is just the nature of the problem. That's the nature of the beast. Okay, so in the next lesson, we are going to actually continue discussing Lagrange multipliers. We'll do some more examples. We'll pull back a little bit, so we'll discuss some of the geometry of the solutions, and we'll try to make sense of what's actually going on. Again, not theoretically, we just want this to seem reasonable to you, that we didn't just drop this in your lap and say, use this technique to find max min for a function subject to this constraint. We still want it to make sense. Okay, thank you for joining us here at Educator.com. We'll see you next time. Bye-bye.